Are we
ready? Gracias.
Perfect. Okay, welcome everybody. And now we have our next lecturer. It's my great pleasure to introduce Armando Faz. Let me give you a brief summary about his work. He's a computer science researcher focused on public key cryptography and its use in engineering applications. His research interests are on elliptic curves and algorithmic optimization, and most recently on post-quantum cryptography. He's part of Cloudflare's research team in San Francisco in the USA. And recently he's been working towards the standardization of hashing to curve methods and the VOPRF protocol in the CFRG working group at the IATF. So precisely, the lecture that Armando is going to give us today focuses on this important cryptographic function that is hashing to elliptic curves. So Armando, the platform is all yours.
Thanks so much for the introduction. As Patrick mentioned, my name is Armando. Well, I'm gonna tell you a little bit more about hashing to curve. So the talk is titled Love in the Time of Hash to Curve, and we're gonna have some very special guests. So our first guest is gonna be Gabriel Garcia. So he was a Colombian novelist who won the Nobel Prize in 1982. And he wrote this novel called Love in the Time of Cholera. And then, well, I'm trying to give some hints about this time, Love in the Time of Hash to Curve, because right now it's kind of popular operation in cryptography. During my presentation, there's going to be some. I expect to have some interaction with people who is attending this live version, and for those of you that will be watching the video after, so I hope you enjoy this too, and then you can skip the parts where I get stuck. Okay, let's first start with the outline of this course. So as we all know, so this is an advanced school. So I will and the talk we're gonna have like 2 hours of the time frame. I expect to cover these main points, but it will be likely that I will take less than 2 hours. So I'm gonna also try to do some some breaks in order to stretch our body. And then, well, so the first section is well, as of course the motivation, and then we continue with what the hashing to curve is and how it is constructed. We continue with the specification and some software implementations that are around. And then we'll see how to use in hash to curve functions. So, well, if everything's okay, I can continue. So can you confirm me if everything's going good?
Yeah,
okay.
All good.
Okay, let's do it. So, well, motivation, let's see what is the problem, and let's see some background. So I want you to be very focused on this part. It's not so hard to follow, and then, well, I will give my best for giving a very good explanation. Okay, so this is a quote that from Gabriel Garcia, who he used to be very popular quoting some famous sentences, and in this case, no medicine cures what happiness cannot. So, okay, so we are all happy right now. So let's start with to see what is the problem that we want to address. Okay, so first of all, we need to set up. So we're gonna working with groups. And a group is this tuple. So we have a set. Please let me know if you can see my pointer.
Yes,
you can see it, right? Okay.
A red dot, yeah.
A red dot, exactly. Okay, so yeah, exactly. So we have here some set G and some operation start and some element E. Basically, this tuple is what we call as a group, and we will use this ball G to denote this tuple. So basically, G is a non-empty set of elements, and the star is a binary operation. So this is super abstract, and then we can think about if we take 3 elements on this set, so we can produce apply the operation star B. So the result of this operation is also in G. So that means that we have the closure property. So we have the identity property if there exists a unique element E, which is the same E that is here, that once that I perform A star E, it will give me this is A, right? All right. So next thing is associativity. So we can group the operation A and B and then apply C, or is the same that applying A to B and C, right? And finally, there's more B inverse for all the elements. So that means that for given an A, we can find another A prime that gives me the identity. Okay, so and finally we say that if this operation A star B is equal to B star A, then we'll say that the operation is commutative and the group is commutative. Well, so here is an important thing about how to see the group. We say that the group is multiplicative or additive. What does this mean? Is about the notation that we have for the group. So if the group is multiplicative, so we will use as E, which is the identity, is going to be the 1. The star, we usually don't use the star, we use the time symbol, this cross symbol. And if we are repeating the operation k many times, then this denotes like exponentiation, right? Which is like multiplying A times A times A times A k times. But if we say that the group is additive, then we change the notation, but that doesn't mean that this changes the meaning of the operation. So in this case, E is going to be the 0, and the operation going to be addition. And when we add many times an element, so we have here one kind of multiplication, but this is a scalar multiplication, where k, remember, is an integer. Well, so in this group, so we can have an element G that we say that it generates the subgroup of G. If we start to using like the powers of G, right? G to the 0, G to the 1, G to the 2, G to the 3. So, and if we continue, we will generate a subgroup of the main group, right? And this is denoted by these angle brackets. Angle brackets G is exactly that subgroup. So what happens? So it happens that if the initial set that when we start is finite, because it's possible that it can be infinite, right? It's but if in this case it's finite, so the group that is generated has a finite number of elements, and we will denote this with n elements. So it has only n elements because it's finite, and this n number is also known as the order of the subgroup, the order of this subgroup. Now we say that the set of exponents, or I mean, all of the exponents is isomorphic to the integers modulo n. Yeah. or if we are working in the additive setting, so we don't say the exponents, we say the scalars. But they are also isomorphic to the integers modulo n. And finally, if n is a prime number, then the integers modulo n is actually a prime field that we will denote like this. So what does this mean? So basically it means that if, remember that we have g to the 0, g to the 1, g to the t, and if we continue, it seems that this sequence of operation, it will not end, right? But we just mentioned that because the group is finite, so this subgroup must be finite. So it must happen that at some point we get to this g to the n minus 1, and the next time that we multiply times g, it will return to g to the 0. So we have this kind of cycle here. And this many numbers of this number n is the order. So it is the integer that makes me to return to the identity. All right. Okay, so we have a very important property here, which is the discrete logarithm. So we have a group G that is generated by this little g, and it's order n. So the discrete logarithm of any other element in the base G, so remember G is our generator, it's gonna be an integer such that H can be expressed as a power of G. So we, many of us will remember this formula from our school, that the log base G of H is equal to the exponent of G, right? Which is equal to X. So basically the same properties follow like that we are used to. Basically the logarithm of the unity is 0. So we need to raise A to 0 to obtain 1, right? So we need to raise A to the 1 to obtain A. Here we have another property. So basically the exponent here can go directly to this side. So basically the logarithm A base A of B times X is going to be equal to this equation. And finally, we can split logarithms. Well, here the numbers BC are multiplying. Here going to be the sum of the logarithms. What happens if we have some other generator? So the problem doesn't change, because basically if we have another generator G2, so we can calculate the logarithm on base G2 based on the logarithm of G1, right? Just calculate the logarithm of the argument of A divided by the logarithm of the base G1 of G2. So there's not much change if we change the base. So it doesn't matter which generator we choose. We're gonna end up on similar computations. Okay, right. Okay, so the discrete logarithm is a problem. Yeah. So basically the problem is super basic. So super basic to state, right? So given a group, a generator, and an element in the group, so we want to find the logarithm of base G of H. However, solving the discrete logarithm problem, this is not easy, right? So there are several algorithms that solve this kind of problem. So first of all, so we have like a exhaustive search. So this is gonna take us a lot of time, like linear in the size of the number of elements, right? If we have n many elements and we want to try one by one, so we're gonna take a linear time on the number of elements. So can we do better? Yeah. So we can use like the baby step, giant step algorithm, and then that will reduce the time complexity by a factor of 2, right? Is the square root of on the size of n. But it not that it's both for time and space complexity. So we need too many time and too many memory to execute this algorithm. Is something better? Yeah. So for example, the polar row. So the polar row, it requires it has the same time complexity, but the space complexity is now improved. There are some other special algorithms like Poly-Hellman. This is useful when n has many factors, or there's the index calculus algorithm, which is actually sub-exponential on the size of n, but only it can only be applied to some special groups. There's another very powerful, which is short algorithm, which actually is it's a quantum algorithm that can solve very efficiently a discrete logarithm problem. Fortunately, we will not we will not focus on quantum algorithms, so we can survive at least for the rest of this talk, choosing n as a prime number and be exponentially large. So let me know if you have questions or you have comments. I am reading the chat right here, or I can see your reactions at least. What are some groups? What are some interesting groups for cryptography? Well, there are many. The most simple is the multiplicative group of integers modulo prime. So you have all the integers, reduce modulo a prime p, and take the multiplicative group, which is denoted like that. Or you can ask for a special modulo prime p, 2q plus 1, where both p and q are primes. So this is it has a very special structure, which is sometimes useful. So we can ask for the multiplicative group of the finite field of q elements. So this is another interesting group. I'm just mentioning what are groups that are commonly used on cryptography. Then I'm going to focus on more interesting group. We have also the quadratic residues of integers modulo n, where n could be prime or composite. There are some crypto systems that work on that. But the one that is more interesting for this talk is the group of points on an elliptic curve. And this is going to be like the focus of our presentation. There's another group which is like a generalization, which is the Jacobian of an hyperelliptic curve, which I think is too much for this talk. So let's focus on elliptic curves first. Okay, so what can I do with a group? So if I have a group G, so I can do public key encryption. So for that, as always, what I need is a group G generated by G for their n. The key generation, so the user has remember a pair of keys, one private key, which is X. Is just this notation means that is chosen at random from this set, basically the integers modulo n, and then I choose one of them at random. And the public key is going to be like G to the X. I take the generator, raised to the power of X, and then the element that I get is, I will call it Y. That's going to be my public key. So how do I encrypt a message? So basically, if I have a message, like, like my email, like a letter, or like a tweet, so I need to encode the message as an element in the group. So in order to produce this n prime, I need to choose another auxiliary value k at random from this set. And the ciphertext is going to be this pair, gamma delta. Gamma is going to be the generator to the k, and the delta is going to be the message prime times y, which is the public key, times raised to k, to this value that I have. So remember, I am protecting this message with this in order to convert it in this ciphertext. How can I do the opposite? So, well, I can do decryption of this ciphertext in order to recover the message. So first of all, that I need to do is like calculate the M prime using this formula. Basically, it's gamma to the minus x times delta. So if you follow the equation, you're gonna see that this term, which comes from gamma, cancels out with the term that is on delta. And then if we are able to cancel these two quantities, so we get M prime, which is what we want. But we also we also need to recover M from M prime. So this is one interesting function that we have. So basically here, most of the operations are well known. However, this codification, how to encode M like an arbitrary message as an element of the group, is actually our central operation that we will cover in this talk. Well, so as I mentioned, so we want to encode a binary string, which is denoted like this: is any arbitrary binary string of any arbitrary length into an element of G. So this wasn't like a big problem when G was the integers modulo P, right? For some P, which is a number. So basically, one can use a compression function. So we can basically, given a string, we map into another binary string, but this has fixed length L. So basically, I am compressing all the message into a fixed size string, and then I apply this to the message that I get, and then apply modulo P, and this will give me an element X, which is in the group. So and this works pretty much well when G is this group. However, so what happened when G is an elliptic curve? So first of all, how does it look an element on the elliptic curve, right? Finally, once that I know how are the elements of an elliptic curve, so how can I find them or generate them from the message, right? And also one other interesting question is what happens if F is not a compression function that I described here, but there's also a hash function. And so these are main questions that I want to discuss right now. And then, well, let's start with some other motivations. So why this is really important? Well, for example, we have this WPA3 protocol, which replaced very recently the WPA2 protocol, which is used in Wi-Fi connections. So, I mean, we use Wi-Fi everywhere in our houses, in the office, in you know, on the streets, on the airports, and then the protocol that protects the information is under this standard WPA2, and that was recently updated to WPA3. However, there was an attack that was called Dragon Blood, which is an attack to WPA3 by Van Hoyen and Ronen. And this is like the website of the attack. And where it fails there. So guess what? So basically it fails the way to encoding points into an elliptic curve. So basically, I'm going to give you more details later on the talk, but basically they can recover. So as you can see, I'm just did a screenshot of the paper. It says figure 6 shows the distribution of the return values of the field of iteration of hash-to-group algorithm, which results in a distinguisher whether it's a non-QR number or when the first iteration results in a QR number. Basically, the attacker is able to detect between these two situations. I'm going to show you later what does this means, but basically you can see that the probability of values is different whether it's in the class red or it's in the class blue. Some values are more likely to appear when they do measurements than others. And this can help the attacker in order to recover keys and mount an attack. All right, so with this motivation, so something that I want to highlight with WP83 attack is that this is not only theoretical. So, I mean, it comes from some part that is very theoretical and has some, the other end, which is very practical, and which is like, you know, an attacking of the keys and a revealing of the keys and the keys that everybody of us uses every day, like Wi-Fi and some other protocols. But I am highlighting this because it has some relevance on our lives. So right now, so I'm going to start with some background, like very regular definitions about what a hash function is, what are finite fields, and what are elliptic curves. Why we need this? Because I need to have to establish some notation first, and also establish some concepts. And for those of you that are not familiar with this concept, okay, so you can get remember a little bit of these concepts. For those of you that are very, very familiar with this, so please be patient. So it will not take so long. I hope so. All right. So okay. So, oh, yet another quote. So, does anyone wants to read out loud? So, any volunteer to read the quote? I mean, I did first one.
Sure, I'll do it.
Okay.
Let's see. It says, what matters in life is not what happens to you, but what you remember and how you remember it. Very nice. Yeah, it's very nice. And guess what? Guess who was the author, right? So our special guest, Gabriel Garcia. And then, okay, so let's see if everybody of us remember and how well we remember our basic concepts, like, for example, in hash functions. Well, thank you so much, Patrick, for reading the quote. There are going to be more. I hope there's different volunteers next time. I appreciate that. So, okay, so the cryptographic hash function is basically a function that takes an arbitrary a string of arbitrary length and then gets mapped into the fixed size binary string. So additionally to that, so basically this is like a compression function, but we also want some other properties. So basically there are three main properties. The first one is pre-image resistance, is that given some string y, it will be difficult to find x such that when I apply the hash function on x, it will be equal to y. So basically, if you give me the output, I'm challenging you to find the input that makes this hash equal to y. A different property, which is very related to pre-image, is the second pre-image resistance. So here, someone gives us the x, which is an input, and then they challenge us to find an x prime such that they have all the same hash value. So they have the same hash value, but they are different. So the inputs are different, and then I'm trying to find one collision here. And another property, which is
very, very important is the collision resistance. So in this case, I don't have an input. The input is a hash function, and I need to find pairs like x and x prime such that they have the same hash and they are different. So in this case, it's totally finding the collisions, but in this case, it's like find one collision for this given element. Well, it is likely that this happened, right? It is likely that collision can exist because remember, H, the hash function, has an infinite domain. What does this mean? Is that it can be any string, like any length, and you can choose it. It doesn't matter. And then we are like mapping this to a fixed size string. So it will be very likely to get collisions. So we know that, right? But what we need from this hash function is we need that this hash function be this collision must be difficult to find them. So yes, we know hash function will have collision, but maybe it will be challenging to find these collisions. There are some standard hash functions, of course. There are some based on Markov-Damgard construction. So we have some deprecated function. Please don't use it. I'm just listing here because of historical reasons. MD5, SHA-1, and then forget about it, don't use it. So we have SHA-2 family, which is kind of the most popular, very well-known function. So basically, it has two parameters, which is the block size, is how many bits it can take from the input, as the Markov-Damgard construction is an iterative function. So it can consume, like, for example, for this case, 512 bits at each time, and then at the very end it outputs 256 bits. And the same parameters, the same methodology for the parameters, it follows for the other cases. We also have SHA-3 family, which is not based on a Markov-Damgard, but it's based on a sponge on a sponge construction. So basically, we have also we have several functions, but I'm listing here the more used or the more important, let's say. As you can see, the block size here as the security increments, it takes less input per time, but the output size it remains the same as in SHA-2. So they are kind of they're trying to mimic the output size. However, SHA-3 also defines some other nice functions, which are the extendable output functions. And then, well, let's see what is that. So, extendable output function is very similar to a hash function. However, the output is variable, so we can request as many bits as we want, and it's not a fixed length. So why we need extendable output function? Well, sometimes we need to replace multiple invocations of a hash function, or sometimes we compute like the hash function and then we truncate some bits. So these two cases are frequent to happen. So for this case, we have these two functions, shake 128 and shake 256, which are standard XOFs. However, the security strength depends on the output length, of course, right? If we request a few bytes, so it's more likely to have more collisions, and of course that makes more insecure. So basically, for example, if you can see, like for SHA-256, the collision resistance basically is half of the output size, the same for SHA-3. But for the shape, which are extendable output functions, is this minimum, or it can be 128 bits, or if you request less than 128 bits, then that's going to be half of that. And similarly for the last shake. All right. Okay, so let's move on to finite fields. So we also need finite fields. A finite fields, basically it has characteristic P, which is a prime. It has order equal to P to the M for some integer n. In a finite field, we have two operations. Remember that this is more powerful than a group, because in the group we only have addition, but in the finite field we have addition and multiplications. And all the non-zero elements have inverse, which is a distinction between rings and finite fields. So we have these special cases with P is equal to 2 or 3. We'll say that we are working with binary or ternary fields. And if P is bigger than 3, then there are fields of large characteristic. And these fields are the ones that we were going to work on. So what happened when M is 1? So when this exponent here is 1, so basically Q is equal to P. And then we have prime fields, and they are isomorphic to the integers modulo P. So the elements are represented in this set, so all the integers between 0 to P minus 1. The operations are as usual as integers, but they are just followed by modulo P. Sometimes some people denote the prime field like this. We will follow this notation, but some other people denote like Galois field for their P. What happens if the exponent is bigger than 1? So in this case, we have F is going to be an extension field. That means that an element in this field, it can be represented in polynomial basis as a vector. A vector with m entries, which each entry is defined in the prime field. And we also have a basis, which basically are the coefficients of this polynomial. We can use any basis that we want because all of them are isomorphic, but some of them are more efficient than others. And here the operations are as usual as polynomials, but in this case modulo F, which is another polynomial, an irreducible polynomial in F. Well, so what are the operations that we can do in finite fields? Well, as I mentioned, well, addition, multiplication, and this is cool, but there are some other interesting operations that sometimes we don't take too much attention, but well, I'm gonna dive into this operation: exponentiation, inverse, quadratic residues, square roots, sign, and the storage. Okay, let's start. So exponentiation, basically, it means if we have an element on the field, so we want to calculate a to the k for some integer k, and this is one very basic algorithm to do that. It is called double and add, and basically it consists on representing the power k in binary, and then iteratively either initializing this counter, which is going to be the output equal to 1, and then basically it's going to scan in the bits of this number, and in this for loop it's going to create the powers of 2 of this number, and whenever the ki bit is going to be 1, so it's going to multiply times a. At the end of this loop, so b is going to be the result of a to the power of k. So the cost here is based on the number of on the size of k, and on average it's going to be like log k many multiplications and log k many squares. All right. So what about the inverse? So we want to, we have an element on FP, and we want to calculate the inverse of this number. So we have one way to do it is using the extended Gcd algorithm. So basically, the property here is that for any a that I choose in this field, in this prime field, the GCD of these two numbers is going to be 1. So they are coprime. And computing the extended GCD, it means that basically there exists these u and b numbers, which actually completes this equation. So a times u plus b times b is going to be equal to 1. This one is this same one. And when I take modulo p, so I can get rid of this term because vp is a multiple of p. So I can find that the inverse of a is going to be u. So if I apply the extended GCD algorithm to find u and b, so I can discard b and get the u value, which is going to be the one that multiplied times a, going to give me 1. So this is one method. So one other method is going to be following the Fermat little theorem. So this is a different construction. Basically, it says Fermat little theorem says that it exists an integer k that when I raise a to the p minus 1 and subtract 1, going to be a multiple of p. Once again, taking modulo p, I can get rid of this term, and basically it says that a to the p minus 1, it will be equal to 1. And when I divide times a, I'm gonna get like I'm gonna discover that the inverse is gonna be the inverse of a is gonna be equal to raising to p minus 2a. So here we have two methods. One of these is based on GCD. The other one is based on exponentiation. We already know how to do exponentiation. So these two methods are different in the sense that here the GCD internally, what it's doing is just additions and subtractions, while in the exponentiation is just doing multiplications. So because of that, this method is gonna be more costly. However, the GCD algorithm is actually faster, but it can be vulnerable to timing attacks because its time it depends on the inputs, and in this case, it's not. Okay, so we are starting with some more interesting property of the field elements is not all the elements of F can be expressed as an square. So basically we say that an element A is a quadratic residue in F if there exists an element R such that A can be written as R squared, right? So R is like an element that when I multiply by itself, I get the A. If I can do that, so if I can find this element R, so I say that A is a quadratic residue. But if I cannot find it, so I say that A is a quadratic non-residue, or QNR. So we have this this table. So what happened with all the combination, whether A is QR or QNR, A and B, and then I do the multiplication of that. So basically, if both are have the same quadratic residuosity, so if both are quadratic residues, I'm gonna get a quadratic residue. Or if they are non-quadratic residues, I'm gonna get a quadratic residue. But if they differ between them, so the end result, I'm gonna get a quadratic non-residue. So clearly, 0 are 1 and 1 are QRs. So does anyone have think about what this is true? Of course, right? Because the 0 can be expressed at 0 square is going to be 0, and 1 square is equal to 1. So I am finding some elements for which I can express this as an square, which are themselves, right? So they are QR. So this is the easy case, right? So what happened when P is prime? So they're gonna be like exactly half and half. So I'm gonna have P minus 1 over 2 quadratic residues and the same number if I consider like all the elements and removing the 0, right? So I have this partition. I have I just put some links in order, if you want to see how this, what is the distribution of these quadratic residues on the finite field. So basically, these are like animations of that. I think I continue because better to continue. You can click and then you can check it later. So how do I know if an element is quadratic residue or not? So in the case of prime fields, this is easy. It's just I have one method which is computing the legendary symbol, which by definition the legendary symbol is of A and P. Is the result of this legendary symbol is going to be 0 if A is 0 modulo P. It's going to be 1 if A is a QR, or it's going to be minus 1 if it is not. So basically, the way that computing the legendary symbol basically tells me whether A is QR or not. So there's an algorithm very similar to the GCD to compute legendary symbol, and then, well, we can adapt like the GCD algorithm to compute legendary symbol, or we can use the Euler's criterion. Basically, this is an exponentiation. That means that if you have A, and if you want to know whether A is QR or not, you can raise to this power P minus 1 over 2, and this gonna be guaranteed that that's gonna be 1 or minus 1. If it is 1, that means that A is QR. Otherwise, it's quadratic non-residue. So once again, I have one method that is based on GCD, and I have another method that is based on exponentiation. All right. So I know that. So with this testing, so I know that A is QR, right? So if I know that A is QR, then I can extract square roots. If A is not is a quadratic non-residue, so there's no square root for that. Okay, so I'm gonna assume that I have all I have an A which is a QR, and I want to compute the square root of that because I know that already contains a square root, right? So, and here is where things gets a little bit more complicated. Basically, if the finite field has size Q equal to P to the M, and M is odd, and Q is congruent to 3 mod 4, I have this formula, right? So basically, if I have all of these conditions, M is odd and Q 3 mod 4, then I can compute the square root of A equal using this exponentiation, A to the Q plus 1 divided by 4. so this is a very nice formula, right? Because I have just raising to this power and I get the square root. But this is only restricted to fields of that are 3 mod 4. So what happened with the other fields? So we have another algorithm, which is Atkin algorithms. So for the class of finite fields that have that are connected to 5 mod h, so I have this algorithm. But as you can see, it gets more complicated, right? So here we have like one exponentiation, and here we have something more difficult. But let's see basically what it does. Basically, it says, okay, let's try to compute this root candidate. Let's say this root 1 gonna be a to this power q plus 3 divided by 4. And if this is the root, I mean, if you can test that R1 square is equal to A, then you return this root candidate, right? Because you just made the test and then you are done, right? But if this test failed, so you can multiply R1, the root that you just computed, times the square root of -1. So we are assuming here that the square root of -1 can be computed very easily, right? Because we are fixing the parameters. Yeah, otherwise this is like a recursive function. But this is not the case. So basically, we have here two cases. We compute one candidate root R1, and if this is the one, we return it. If this is not the case, we can fix it. And we can fix it multiplying by the square root of -1. So as you can see, there is this, the difference between here to here is that here we have just one candidate root, and this is the one that works. Here we have two, and for the next algorithm, which is, for the next case, which is Q congruent to 9 mod 16, we're gonna have 3 candidates. And if we cannot attend all the queues, finally we use Tony-Leshan's algorithm, which is a generic algorithm for computing the square roots, which is much more complicated that I'm not listing here. But the thing is that I want to show here is that depending on the equivalence class in which Q is, basically we have a simpler algorithm, or one more difficult, or one much more difficult, or we just end up with the generic algorithm. Well, this is going to be important in later, a little bit later. So there's so we have here M odds, but what happened in the general case? So I'm using this this diagram from this paper from Ash and Rodriguez, and then so basically they provide a taxonomy of square root algorithms. So they cover basically all the cases, whether M is even or odd. We just evaluate this M odd in the previous slide. So, but in that paper they give you some pointers to all the different cases. We just saw this branch, right? Like when 1 mod 4, 5 mod 8, 9 mod 16, and 1 mod 16. So I recommend you, if you are very interested in what is the exact algorithm for computing square root, so you can check these two papers. The Scott paper, basically, it gives you many tricks that you can apply, many algebraic. So the problem. So the square root operation is what output. That means that it can return one output in a set of different outputs. So let's see with this with an example. So if we have r, which is the square root of a, then we know that minus r is also the square root, right? Because, well, we can check it simple, right? So both of these quantities are square roots of a. So if I have an algorithm that solves the square root operation, how do I know which root to choose? So this is the concept of principal square root. So I have a square root, which is the principal, which is the right root. And basically this criterion, or there are several criterions to define the principal square root. So this criterion is, for example, that the root that I chose is also a QR. So this is interesting because one of the roots can be in some fields is also QR. One another criterion is that I choose the positive root. Of course, this works on the integers, right? Because on the integers we have like positive numbers and negative numbers. But this may not work on finite fields because all the numbers, let's say, are positive, or there's no negative numbers. And in this case, well, this is another criterion. Rather than choose the positive root, choose the non-negative root. And for this, there's a definition for that. Yet another criteria for choosing the square root is the parity bit. So I'm gonna dive on these two criteria. Okay, so we have a prime field again. So we can compute the sign of an element. Actually, we are defining here. So this is a definition. So if the element is on is between 0 and p minus 1 over 2, so we say that this element is not negative, right? It may be said it's positive, right? Many people want to use like, double negative. Between p minus 1 and p minus 1 over 2 on up to p. So we say that that number is negative. If we can have like a mental model about what does this mean, is that suppose that we have here the 0, and here are all the numbers that are in this case non-negative, let's say non-negative, which are between 0 and p minus p over 2, let's say, and the others are negatives, right? So basically this is partitioning the set in two halves, of course, but all the elements are like all the elements on the same class are together, right? So let's see what happens with the parity. With the parity, it is defined as you take the element, you compute modulo 2, and of course, if it is congruent to 0, we say that the element is even, right? Like in the regular case of integers, even at odd integers. And in this case, we have like we have this a similar partition, or let's say a different partition. There are still two halves, but as you can see, here we have like an even, an odd, an even, an odd, an even, an odd, and this pattern is different. But basically, it can help us to choose a roots when we are computing square roots. Finally, we have the storage. So, believe it or not, this can be a small problem. So basically, if we want to represent an element on the prime field, so we need to first to reduce it into the smallest integer between 0 and p minus 1, and then represent it in base 2 to the 56. 2 to the 56, why? Because we are storing bytes, right, in the computer. So basically this is the same that I mentioned before. So basically I'm gonna have some AI is gonna be bits in the position, in the ith position, right? And how many bits I'm gonna have from this? I'm gonna have B bits, which is exactly this number. So there are two orders. So depending how do you store the bytes in memory. So we have the little endian order. I like this one, which is the byte, the memory byte in the ith position correspond exactly to the byte in the ith position. So this is very natural for programmers or developers as me, but it may not be like very intuitive for some other people when they are to look at the data in memory, right? Or like in a piece of paper. In a piece of paper, we used to write like, you know, numbers in starting from the most significant bit, right? Like if we are writing a number in a paper, we don't write it in the opposite order. And this is why more people are also more familiar with big endian. In this case, the number is stored. The memory byte in the ith position actually stores the last one. I mean the b minus 1 minus I bytes. So basically, this is the reverse of this. Some people like more this, some other this, but this is something that we need to take care because since we are defining a hash function, so we want to specify the things very, very clearly. All right, so I think, so we have this this quote. I'm gonna do some break, like 3 minutes or so. So I have 32 on my clock, maybe 35. It's gonna be okay. If you have questions, if you have some comments, if you wanna go stretch yourself, I totally recommend you to do it now. And of course, I'm gonna need another volunteer for these next quotes. So prepare yourself. All right, welcome back. Okay, so I think we're good on time. I'm gonna accelerate a little bit, but I think I need this background in order to get into the problem. And then who is up for reading out loud the quote that we have? So I need a volunteer.
I can do it. Can you
What's
hear
your
me?
name? Yeah.
Arantxa.
Arantxa.
So age isn't how old you are, but how old you feel.
And how would you feel, Arantxa?
You're asking me?
Yeah.
No, I feel my own age.
Okay. Well, very good. So okay, let's continue with. Thanks so much, Arantxa, for sharing this time. And then okay, so we're gonna start with curves. For those of you who hasn't seen like a curve, so a Weierstrass curve is defined by this equation. So basically, we have let me just find the pointer. We have this equation in two variables, x and y. Y squared equal to x cubed plus ax plus b. This is a standard equation, and it is known as the Weierstrass equation. We want to ensure that this doesn't happen, otherwise we'll get a singular curve, and this is not interesting. Sometimes, how does it look, this curve? Well, if you print like on the real numbers, you can get like different shapes of the curve. This curve is the line on red. So if you're moving the parameters a and b, you can get different shapes. If you want to play a little bit with this, so you can enter to this interactive application, and then you're gonna like it. How does it look an elliptic curve in other domains? For example, in the complex numbers, well, this is an elliptic curve is isomorphic to the torus. We are more interested in prime field. So how does it look the curve in a prime field? So here are 4 different instances. When we have like a small field of 19 elements, so we have this grid. And basically, the points on blue are the points that are on the elliptic curve. So remember here, for example, we have this grid, and the points that are on red are the points on the elliptic curve. Here, the points that are on blue are only the points that are on the curve. And the bigger the field is, we can have more points. But there are going to be some spaces where we don't have like any point. Okay, so okay. So what is interesting is that there's an addition law for the curve, so we can add points using the rule. So basically, p plus q. If we want to add p plus q, so we do this line passing through p and q, and we'll hit the elliptic curve in this point r. We can reflect over the x-axis, and then we're gonna get this other point, and this other point is what we define as p times q. We can also intersect the curve in a single point, forming like the tangent of the curve at p, and then we hit in another point r, and then when we reflect, we're gonna get p plus p, which is 2p. Basically, if I have a point on the curve is symmetric on the x-axis. So basically, the x and minus y is also a point on the curve. Okay, so we have rational points. So that means that this is just another way to say that we are interested on the points that are on the that satisfies the equation, and also we need to add this other point. Why we need to add this other point? Because with this definition, we can find that the curve defined on F is actually a group with the point addition with this element, with this extra element as the identity. As I mentioned, the order of this group is as large as the order of FQ. We saw that in the diagram with the dots, with the blue dots, and basically this is the hash interval, which basically says that the number of points is bounded between these two quantities. And of course, there are efficient algorithms to calculate this number. So how do I do addition of points, but not using the Chord and tangent rule, not using a geometric interpretation, but an algebraic operations? Well, there are formulas. Basically, we have a formula if P is different to plus minus Q. So you can just follow these polynomials, and then you're gonna get the X coordinate of the addition and the Y coordinate of the addition. So you can do the same if you wanna do the obtaining 2 times P, which means is addition to P of plus Q to P. You follow these polynomials, and then you get the coordinates. Basically, what I mentioned before is that the inverse of P is just it's just negating the Y coordinates. By definition, we have that this 0 element is the identity, right? So we know this equivalences. If we add 0 plus 0, we get the 0. If we add to some point the 0, either on the left or on the right, we get the same point. It doesn't get altered, and the inverse of 0 is equal to 0, right? So we need to consider these special cases because this point is an artificial point. So at this point, we don't know what it is, but we need to take care of this. And this is kind of something that we need to take care of. But, well, we will see how to handle this case. And we can handle this case because, I mean, we cannot handle this case right now because we are working in an affine space. That means that we are working on coordinates, on n coordinates. But if we move to a projective space, then we can add an extra coordinates. Here the coordinate goes from 0 to n. And in this projective space are all the tuples such that xi are in F, but we restrict that all zeros is not here. Basically, in this side we have an equivalence relation that says that 2 elements are equivalent if one is the multiple of the other. So we can have many different elements that represent a single one, right? So in this case, we can put the finite space inside on the projective space. Basically, if I have n coordinates here, but in the projective space I have one more coordinate, so I can copy the first n coordinates, and for the last one I just set 1, like saying fixing this coordinate to 1. Can I do the opposite? So given a projective point, can I get the corresponding affine point? Yes, of course. So basically, I copy the first n coordinates, and each of them I divided by the last coordinate. In this point is equal 1. So when divided by 1, it doesn't get altered. But if it is different to 1, so I can take advantage of the equivalent relation to get the same point. The only exceptional case is if this is 0, right? If this last coordinate is 0, and if this is the case, we know that we say that this point is at infinity. So all the points for which this coordinate is going to be 0 are points at infinity. Well, so what happened when we map the curve to the finite space? Well, this stays like the same. So we're relabeling the variables. So x going to be x1, y going to be x2. And when we move to the projective space, so we get this this formula and relabeling. So we have one more coordinate, x1 going to be big X, x2 going to be big Y. And we have this x3, which is the additional coordinate, which is going to be big C. So with this, if we think about like the previous definition of the rational points, but now in the using the projective equation, you can see that there's no extra point that is added here because 0, I mean, this 0 point is actually a projective point. So this point is projective, and it happens that it is the only point at infinity that satisfies the curve equation. So we don't need to add extra imaginary points or artificial points because the infinity is a projective and is included in this definition. Why? How can it help us? So, well, in this case, if we want to add points in the projective space or in projective coordinates, so we can do it so, and we have very different algorithms to do that. So we have formulas for projective points like these ones, some others for Euler projection, which is known as the Jacobian projective coordinates. We have Chudnovsky coordinates, Cossette addition, and we have formulas, complete formulas, and complete formulas work for all the cases, including the point at infinity. So we don't need to handle corner cases, and some of them are described in theseeprints. There are different models of elliptic curves. So far I have talked about the Weierstrass curves, but there are some other models of that are also elliptic curves. So for example, the Montgomery curves, they have this shape. As you can see, they have a quadratic term here, and there is no constant term. The twisted Edwards curves they have a very, very different shape, but they are still elliptic curves. And there are some other curves or families of curves that are also mapping to an elliptic curve. There are some subtlety with elliptic curves is that not all elliptic curves produce prime order groups. What does this mean? So remember that I told you that we want that G gonna be the points of an elliptic curve. That is correct. So, however, recall that for security, we want that the order of this group will be prime. So, but not all elliptic curves produce groups of prime order. So, if this is the case, well, we can relax a little bit the requirement, and then we can accept composite groups provided that there is a very big, large subgroup. So basically, the order is now n, which is a composite number, and then we say that R is a large prime, and H is known as the cofactor. And in this case, well, with this relaxation, we can think that the ball G, the group that we want, is not the entire elliptic curve, but this also is only a subgroup, which is a subgroup of large order. So we have here the quality. It could happen that for some curves they don't have like cofactor. there is only one subgroup, or there could be like in this case a small cofactor. Well, so let's get started for hashing the curve. So okay, so that's gonna be simple. So I have one more other quote. So what's up? So we're looking for one volunteer to read the quote. On 1, on 2, on 3, okay, I can read it. So even when the winds of misfortune blow, like when you request some volunteers, some amazing things can still happen. So let's see what are some amazing things that can happen on hash to curve. So first, we're going to differentiate two definitions between what is an encoding and what is a hash function. So basically, they have like the same signature. We have an arbitrary input that maps into a group, into an element of the group. However, the encoding is a non-uniform encoding from a string to points, and the distribution of its output is not uniform. And we also have that it could happen that the encoding also maps to a fraction of the points and not all the points. With this, we know that some points are more likely to be output than others. And this is not something that we want if we want a hash function. If we want a hash function, we want to have a uniform encoding. We want that the distribution of the output be statically close to uniform. So there is no distinction between some points that appear more frequently than others. And we also want to construct some hash function that that requires some random oracle that returns point in this group. So we have these two constructions. So okay, let's see how to construct an encoding first, and from that we can construct a hash. So the encoding, basically, we have the signature, and then we can have intermediate steps from getting from the input to the final output. First of all, I split it in 3 parts, which is the hash to field. We want to hash strings into the field, and then we want to map in the curve using mappings that takes elements in F and produce elements in the curve. But as I mentioned before, some curves have cofactor or some others not. Then we need to clear the cofactor, and basically that takes us from the elliptic curve to the subgroup. If this is the case, that we are targeting our big G. So 3 operations. So hash to field. Okay, sorry. So hash to curve. So hash to curve, as I mentioned, it will be shown a little bit later. So now, how to do hash to a finite field? So in this case, we want to sample numbers in the set of P. When P is close to a power of 2, we can sample elements like binary strings of size B. However, this doesn't apply generally because P is not always a power of 2, and so we can introduce some bias on the sampling method. Also, the prime sizes usually doesn't match the size of the output of the hash functions. And well, one solution is we can use extendable output functions, but we are still using common hash functions because they are widely deployed. And then here the question is how to use hash functions in order to sample elements. Well, one secure sampling is if we have K the security level, so the elements of FP can be sampled in this set with L is going to be like the logarithm, the size of P, plus the security level. So for elliptic curves, P is actually 2 to the 2k. So L is going to be like 3k bits. We are requesting k more bits. This was mentioned in the paper of Breyer in proposition 4. And however, we have the problem that the standard hash function doesn't output 3k bits, like so many bits, right? So we need to do something on top of hash function in order to make them work. So we have expanders. So we have one based on Merkel-Damgard, one other based on extendable output function. The one, okay, sorry. We want that sometimes we want to reuse a hash function because we want to have like 2 different oracles, but they need to be separated or they need to be independent. So for example, we can recycle the hash, we can create these 2 hash functions, H0 and H1, sorry, just by concatenating a A0 or a A1, right? So these H0, H1 are different oracles because the queries that we made using the same methods are different. So we can think about the 0 and the 1 as a domain separation tag, which is just an additional information in order to instantiate different oracles. So, okay, with that. So we have an expander, which is based on Merkel-Damgard function. And so we have the expander takes a message, optionally a domain separation tag, and produces X many bits or bytes. Okay. So if we follow this algorithm, basically it's construct a new DST, we construct some other artificial message, and then we apply the hash on this to get the first block, and then we get a second block chaining the previous block that we just construct, and we do this chaining too many times as we need it, depending on the value of how many bits we want. So we do this chaining operation. The ith block, it depends on the very first block XOR the previous block. And then when we have all the blocks already computed, then we can return the first X bytes from U, from this string. So this construction, it follows the NMAC construction that is given in this paper. Something that is much more simpler is just using an extendable output function. You can see that it's very easily. So you construct a DST prime. You pass to the extendable output function the message, the length, the DST prime, and then you request from the extendable output function X bytes. And that's all. That is the output. So basically the hash to prime field, so we can call to the expander with a message, the DST, and then we can produce C many elements in case that we want to produce different elements on FP. So that returns C elements, and then C strings that we can reduce modulo P and get the UIs that we want on FP. How can this be extended to finite fields? Well, this is we need to request n times more bytes, so multiplying here times m, because remember that elements on extension fields are vectors. So it's pretty straightforward to expand from here. So now that we know how to do hash to finite field, we want to know how to map into the curve. So these are examples of how not to generate points on an elliptic curve. So these are bad examples. So first one notation here. So I'm gonna introduce this g to the x, which is like a polynomial, like the polynomial exactly this x cubed plus ax plus b. Well, So, so the first algorithm that doesn't work is trial and error. So we can sample an element x at random and then calculate g to the x, right? Which gonna give us a y value. So basically, if y is QR, then if this value is QR, then we can return x. So the x coordinate that we have and the square root of y. Here is an error. The square root of y, and that's gonna be a point of the curve. But what happens if y is not a QR? Then we fail. So is this secure? Is this good? No. Well, it's actually a probabilistic algorithm. It succeeds only with y is a QR. So we want something that be more deterministic, right? That doesn't fail. So there's the second intent on how not to generate points on the elliptic curve is the try and increment method. Basically, it follows the same structure. We just add in some counter here, and then we perform the same operation. If y is QR, then we return x and the square root of y. But if it is not a QR, then we increment and then we give it another chance to our algorithm in order to not to fail, and then we go to the step step 2, and then we sample a different. Sorry, step 2. We go to step 3 to calculate again another y. So in this case, we are giving more chances for the algorithm, and then eventually we'll return in this 4.1. However, the time, although it succeeds, we don't know after how many iterations this will end. So this is a non-constant time algorithm. So remember Dragon Blood? So this is like the code of that is used on WPA3. Basically, it has the same structure. So basically, if this value is a quadratic residue and this is not found, then we can choose another value, and then we can iterate this in this while loop until we find a value that is a square root, and then we return the point. Basically, here this a timing attack that I showed you the figure before. There is more probability to whether the value is QR or not, and this can be used to mount an attack and recover some keys. Well, so in order to avoid this problem, so what we want to have is some deterministic mapping that takes element in F and always generate a point on the curve. So there are some algorithms well known. One of the first one are the Scalves equations. However, it has a disadvantage that they are polynomials of very large degree. Another is the ICARS method, which only applies to fields which are Q congruent to 2 mod 3. So it doesn't apply to any other fields, only to these ones. And there are some other algorithms that can be used, but not all of them are so general. They have some parameterization. So the first one is shall we find the Westy. Basically applies to almost any elliptic curve on this form, but it has some additional parameter C, which must be different than 0 and must hold all of these properties. Basically, this algorithm applies to all the curves, provided that this C element can exist. However, the disadvantage of this method is that it computes like 2 square roots, and square roots are hard to compute, remember, because we are computed with using either all the algorithms that we saw before, or in the worst case, we solve it with Tonelli chunks. So this algorithm is costly, but it's some kind of generic. So there is one simplification, simplified SWU mapping, which is a simplification of the previous algorithm. So basically, we also have this C element, but as you can see, the restrictions on C are more simpler. And however, A and B cannot be 0. So A or B cannot be 0. So, okay. And it is also simpler because it just only computes one square root. So it doesn't require 2, it at most requires one square root. And this is good. So what happened when A or B are 0? Well, there is this technique. What if we find an isogenous curve, so an additional curve for which A and B are not 0, right? So we can apply the previous algorithm on the isogenous curve. Then we apply the isogeny in order to move from the alternative curve to the curve that we are interested. And this works, of course, this works, but it has an extra cost, which is performing the isogeny and finding the isogeny. Well, so there is the alligator 2 mapping. This applies to Montgomery curves of this shape. So here we don't need a C element, but we need an R, which is a quadratic non-residue. And for any input U, so we can compute these 5 operations, and then we get a point on the curve. As you can see, there is one inversion here, one square root here, and one legendary symbol computation here. So this looks as very costly, but actually there are some tricks that you can apply in order to get all these operations in one. This doesn't apply generally, but at least for this scenario, we can reduce everything to one single exponentiation. So what happened with twisted Euler curves? Well, in this case, we apply alligator to the Montgomery curve, which is associated to the twisted curve. So we apply alligator on input U, we get a point Q. We apply the birational equivalence that maps points on Montgomery to points on twisted Edwards. And basically we have P, which is a point on the twisted Edwards curve. So this is very convenient to take advantage of this equivalence. So finally, clearing cofactor. So the output of a mapping, like the ones that I mentioned, it could be any point, right? It is not guaranteed that the point be in a specific subgroup. So in this case, for example, when the points on the curve is a prime group, so the cofactor is 1. So we don't need to do any operation on that. So clearing cofactor is equal to nothing. However, some elliptic curves, as I mentioned before, they have some cofactors. So in this case, as I mentioned, n is gonna have a cofactor, and then if we have the respective generators of each subgroup, so when we have a point, we actually have a linear combination of these generators for some integers k1 and k2. So the easiest way to get right to get a point in the main subgroup is multiplying times the cofactors. It's very easily that when I multiply h times p, this value is gonna be cancelled because g is of order g1 is of order h, so that means that this is gonna be equal to 0, and then I get a point in the main subgroup that I want. That is the subgroup that I want to work on. Well, what happens if P already belongs to the subgroup of order H? When I multiply times H, I'm gonna get the 0. This is not too much a problem because 0 is still an element of the group. And if P already belongs to the subgroup of order R, and then I multiply times H, so it's gonna get this. I still get a point on the curve because the group is closed. And the cofactor multiplication becomes a permutation, right? Because I'm just moving elements here inside of this group. That means that multiplying times the cofactor removes the points of the small subgroup and permutes the points that are in the large subgroup. And the cofactor can do this, but if we multiply times a multiple of h, it has the same effect. This has the same effect. So there is a faster method in order to multiply, to clear in cofactors, but without multiplying times exactly h. And then for example, in pairing friendly curves, multiplying by a multiple of h is much more efficient. So why? Because actually the scalar is written in base p, and in that curves, powers of p are performed by applying the Frobenius map. So in that case, we can find for a good multiple of h, such that the composition be easily to solve. So finally, we have the encoding to curve. We have constructed this function from binary strings to elements of an elliptic curve, following these three main tasks. Basically, we hash to the field the message, domain separation tag, and then we request just one element. This element will map it to the curve. That's going to give us a point. And for this point, we clear the cofactor, which is going to give us p. Now, how can get a hash to curve from this? So here's the question: can the encoding be used to do a hash? So basically, this notation means that we are using like the hash function, and then we apply the encoding, and that's all. So is this enough? So the question is, the answer is no, because as I mentioned, the only the output of f doesn't reach all the points on the curve. And also it's not uniform, because some points are more likely to appear than others. And we can distinguish very easily if the point comes from an encoding, or whether it's a point chosen at random. So can a scalar multiplication be used as a hash? So in this case, we first hash the message and then multiply times a generator. So the answer is no, because in this case, we know what is the discrete logarithm. So we know h of m, which is the discrete logarithm of the output, and we don't want to have that, because otherwise make some protocols insecure, such as identity-based encryption. Okay, what about the combination? Let's use the encoding here, and then let's use the scalar multiplication, and then add together the results. So this works. Yeah, it works, but has some disadvantage that it requires a full scalar multiplication. Usually the scalar multiplication is much more costly than evaluating the mapping. So can we do better? Yeah, okay, let's get rid of the multiplication and then just call the encoding twice and then add the output. Does this work? Yes. So because Breyer and et al. Showed that this construction actually is a hash function. However, they proved that only applies for the ICAR mapping. So we are not completely satisfied right now, but let's see what happened next. So some years later, Farashahi and other authors, they showed a more general construction. Basically, you need to add as many outputs of the encoding, you add together. What is this S? S is something that is bigger than the genus of the curve. For simple term, in the case of elliptic curves, genus is equal to 1. So S, any number that is bigger than 1, so S is equal to. So we need to only add two things, and then encode twice and add is the way to go, because it works for elliptic curves, and then it's proved that is going to be a hash function. So this is the algorithm. Basically, the strategy is now, as always, I hash to the field the message, some domain separation tag, and in this case, I requesting for 2 elements, U1, U2, and then I apply map to curve to the first one, map to curve to the second one. I get 2 points. The output of these 2 points, I can add them, and then the result of the point, I can clear the cofactors and to get the final result. So basically, this is the construction of how to do a hash to curve securely, following all the steps that we have defined before. And this is like a diagram, whether you want to start from a message into a point on the group that you want to target. Basically, the first question that you need to ask to yourself is whether this hash function is going to be used in the random oracle model. If you are very sure that this is not the case, then you go with the encode to curve, which is, remember, hash to field, then map to curve, and then clear cofactor, and then you are done. But if you are not sure, or you are sure that you need a random oracle of points, then you need to apply the hash to curve construction, which is basically the hash to field. You request 2 elements, and then for each of them, you apply the map to curve on each. You get 2 points, you add them together, and then you clear cofactor, and then you are all set. So, all right. So, okay, I'm gonna go through the specification and software. So this is another quote. No matter what, nobody can take away the. I can see the last part. That you already had. And well, let's see.
Armando, is it possible to ask a question, or should I wait to the end?
You can ask a question right now. Yeah.
So before, what? So I didn't understand, why do you need two points on the curve? So like in the construction hash to curve, why do you do this with 2 points?
Basically, it's because of this proof, right? Remember that this was a more general construction, that it says that you need to add as many encodings, right? And this S is related to the genus of the curve. And since the genus of the curve is 1, S is equal to.
Okay, okay. So if not, it would not be correctly distributed.
Exactly.
Right?
Exactly.
Actually, you have the case, Armando, when you don't add, right? It's a problem. Yeah. What happens if S is equal to 1? If you don't add, if you only have 1?
Well, that's what happens, that I'm gonna working on a curve or in something that is genus 0, like the circle, for example.
No. What would be the problem in knowing this result if you don't add several F's, just one F? If you're lazy.
If I just take this, right?
What would be the problem?
The problem, it was shown.
That's my point, that you discussed it before.
Yeah, it's gonna reduce to this case, right?
Exactly.
And in this case, the output of the hash is gonna be the output of F, and the output of F doesn't reach all the points in the curve.
That's the problem, distribution, right?
Yeah.
Yeah. Thank you very much. Thank you.
Yeah. So yeah, this is why this is not secure for a hash, right? And then we do this basically for elliptic curves, and we add as many terms for hyperelliptic curves. Okay, this is where we need these 2 points, and then the specification. So we need the specification because there are many scattered references about how to perform hash to curve securely. Most of the words are from the math, from algebraic geometry branch, and they are very difficult to grasp. Even this presentation that I tried to do for you, the more simpler, I'm totally sure that some things are not very clear, but anyway, you can take a look at the papers, and that's going to be much more difficult to get. And the worst of this is that the insecure algorithms are the most popular. So we need to do something in order to fix that. So that's why around 3 years ago, there was this proposal of an internet draft, CFRG, of the Internet Engineering Task Force, EITF. So this is a draft that specified algorithms for hash-to-curve. Currently, we have in the iteration 12. So this document since then has been updated, and we are very close to the last call. That means that we are freezing the algorithms and the options. And if you want to be part of this, so you can get subscribed to this list, and then you get some news about, or you can participate in the discussion. So this is an open discussion, and anybody can contribute. Well, so the internet draft, as I mentioned, defines some cipher sheets, which is like a set of algorithms for well-known curves. So basically, a cipher sheet defines what is the curve, what are the parameters, what is the main group or subgroup, depending on the curve, what is the hash function that's going to be used, what is the best mapping for the curve. And then we also provide some pseudocode for optimized implementations. And so this is good because you have in one single document exactly the function that you need to implement in order to fulfill the hash-to-curve. There are some cipher sheets for very popular curves like Nis curves. There are also for curve 25519 that there are used in Diffie-Hellman, also for twisted Edwards curves, used in EDDSA. Also, we're considering the curve, the Bls curve P256 for that is used in Bitcoin, and we have one example of a pairing-friendly curve, which is the BLS12. So, is this frozen? No, because we have we describe a method in order to define new cipher sheets, and we also have some section to define interoperability with Decaf-like quotient groups. These are some other groups which I didn't cover in this talk, but they are also interesting. Implementation. So we have the reference implementation. So all the algorithms are written in Python and Sage. There are some test vectors for both encodings and the hash-to-curve. There are some no-answer tests. There are reference implementations also in Go and Rust, and you can find these implementations in this repository. Finally, there are more people trying to join into this or supporting this project with implementing code in their libraries. For example, BoringSL, which is a C++ library. Circle in Go, Ellipsodium, Miracle, Pairing Plus, Relic, Apache Milagro, which it's similar to Miracle. SIG, standard library. SIG is a new programming language, which is was recently proposed. As you can see, there are many different languages. Some of them are the ones that are used most in industry. But we want to expand this list. Finally, okay, here is, let me see how, yeah, I think I can do it. Okay, so finally, as you can see, the evaluation of the hash function is, it can be done in parallel. So we hash twice, and then we apply the mapping twice, and then we add the points. So we can run this in parallel, right? So instead of having one thread, we can split the content in two threads, and then at the same time apply the hash, like a different hash, but in the same message, and then the output of of that, applying the encoding, and then finally recombining here with addition and producing the output. So basically, this part, which is in parallel, that can be parallelized either with threads or with vectorized implementation, and this is something that I did in a previous work. So basically, we have the operation, the hash, the encoding, the point addition, and the conversion, the point to affine. And this is the cost that I have in clock cycles if I do the sequential operation versus the parallel. And this is the difference that I have. For example, the point addition, of course, I cannot do in parallel, right? Because I don't have like any advantage. Also, I cannot do the point to affine in parallel. But what I can do in parallel is the hash and the encoding, and then I get some speed up by running this two tasks in parallel. So finally, when I add up all of this and I look for the final speed up, so I get, if I run this in parallel using a vectorized implementation, that I can get like a 28% of savings. If I put this in a graph, so here I am varying the message length. So as the message that I want to hash increases, I get a different speed up factor. So basically, when I start like for the small messages, the speed up factor that I get is limited. So ideally, I will get like the two factor, because I'm parallelizing almost the entire algorithm. But as you can see, like for small inputs, it is limited, the speed up factor. But as far as I increase the input, I get better speed up. And this is on a Haswell processor. And if I do the same for Skylake, I get more speed up. This difference happen because difference on the architecture. Of course, Skylake is more powerful than Haswell. Finally, well, there are some protocols.
Armando, may I ask a question? Is
sure.
the comparison that you were making, Haswell versus Skylake, it was this is a SIMD?
Yeah, this is vectorized, yeah. SIMD, right.
Okay, and okay, so you're expecting a better speed up on Skylake because the vector instructions perform better, I suppose.
Yeah, exactly. I haven't tested in more recent processors, but I expect like the more recent, the better.
Okay, thank you.
Yeah, okay. So now that we have a hash-to-curve, there are some protocols that we want to use hash-to-curve. One of them is the oblivious PRF, oblivious pseudo-random function. This is a very simple protocol in which the client has an input, the server has a private key, and both server and client, they cooperate to compute this PRF. Basically, it's a PRF under the secret key on the input and produces some output, but it is oblivious. Why? Because the client cannot learn the key of the server, of course. The client cannot learn the private key, but also the server cannot learn the input and the output. So this is interesting how they cooperate in order to the server help to the client to compute this value, but without knowing what is the input, what is the output. And as you can see, this is going to be very, very easily. For example, you have the input and h is your hash-to-curve function. So h of x is going to be a point, right? A point on the curve. And then you can blind it here times r for some random r, and then you send this point to the server. The server, what it does is going to multiply k times p, so multiply times the private key, and then returns q. And then the client, once that gets q, it applies removes the r, multiplying by r to the -1, and finally the output that that the client has is k times the hash of x. So the server cannot learn what is the x value because it's protected by the hash function and by the blinding factor. So this is a very simple protocol, and this is very, very useful. Some other protocol is the Bls Signature. So in this case, we have a private key, which is a random number. Public key is G to the X in a group generated by G. If I want to sign M, so basically the signature is I hash the message, I get a point in the group, and then I raise to the private key. So that's gonna be my signature. And the verification is it uses pairing. So basically I do the pairing of the signature with the generator and check if this is equal to the pairing of H of M, G to the X. And if we follow the bilinear properties of a pairing, we're gonna end up having that the left and the right hand sides are equal. So one other protocol that I will not have time to show you, I just listed here for the sake of the record, and then I will skip it, and then I pretty much finishing the presentation. I just recall this map in order, if you want to encode the curve of hash to curve, this is roughly the way to do it. And the summary, well, I'm working on a concrete specification of hash to curve functions. While doing so, there are many issues because there are different curves, different algorithms, there are full of subtleties. There are very many small issues that need to be solved or need to be fixed. We want constant time and deterministic algorithms. For that, we list in the EITF draft, we want to provide some interoperability between different implementations and that people follow best practices, so people will have like a source of truth about how to do hash to curve. And as you can see, there are many protocols that they require a hash to curve function because they are moving from to curves which are the points of an elliptic curve. Well, finally, I'm gonna thank you all of you, the participants of Advanced School of Crypto 2021, and also I'd like to thank the organizers for the kindly invitation. And if you have questions, so this is the time to do it. Thanks so much.
Thank you very much, Armando, for the nice and thorough lecture. So let's give Armando a virtual applause for the presentation. Thank you very much. We thank you again for accepting the invitation and giving the lecture and the hard work. Does anybody else has a question? This is the last opportunity to do it directly. No? So thank you again, Armando. Yeah.
So
Carla,
maybe I ask
please.
something. So your general feeling is that research, so the important things to research right now is investigating what is the best hashing method for each curve, or what do you think is the most, or do you expect that this will be the end of it, like that you have most of the techniques that, so what is your expectation for the next developments? Yeah, so I mean there are different paths to follow. Right now in the specification we have already chosen some algorithms that at the current time we think are we prove it are like efficient enough, right? But of course, there's always the quest of looking for more efficient algorithms, or that doesn't require like less operations. So optimization is a work to do. The other thing is like, as you can see, there are different curves, and there is no single map for all the curves that covers all the curves. So having like a very general method on the math side, it would be good. Yeah, so
there are also paths to go on the implementation side, try to update the libraries and try to get people aware about these new methods.
So if I understood, for each curve you have a method, but then depending on the curve, it might be less or more or less efficient. No, but there is, for all kind of curves, you have some kind of way of doing this.
Yeah, but I would say for the curves of interest, right? So there are some curves that are standardized, and we are focusing on that mainly. But that doesn't mean that others are not interesting, right? So we focus. I mean, right now we focus more on these cases because are the most used cases.
Thanks.
Good. Are there any other questions for Armando? All right, so thank you, Armando, again.
Yeah, I forgot to share that I have the book.
Ah, I see.
So I'm still reading it, so I'm very close to get it.
Yeah, I watched the movie, but didn't read the book. Probably would be a good idea to read the book first.
Yeah.
All right, thank you, Armando. And now we are gonna go for a long break, lunch break, and are gonna come back around 2 in the afternoon. Thank you very much, everybody.